In this video, we're going to be discussing how we factor when we have special products. So when we have these special products, what our polynomial is going to look like is some unique things. So our first example is when it's the difference of a two squares pattern. And so what that means is we're going to have a problem that looks like this, x squared minus 9. Notice x squared is a square of a number, it's x times x, and 9 here is a square. It's 3 times 3. Now, when we have this difference of squares, and remember difference is referring to this subtraction. So if I have the difference of that squares, what's going to end up happening is I actually have x plus 3 times x minus 3 here. It's always going to follow that pattern. Here's an example of an algebraic rule. A squared minus b squared is going to be the binomial a plus b times the binomial a minus b. And we saw this when we explored special products. We saw when I have something plus b times a minus b, they're a conjugate pair, and so that middle portion there where it's just an x value gets eliminated. And so as we see this difference of squares, we know that this is what our product is going to be, or our factor is going to be. So we want to use this example here to explore it. So the first one is x squared minus 25. I'm going to ask myself, is it a difference? Well, yes. And x squared can be written as x times x, and 25 can be written as 5 times 5. So what does that mean? That I can actually factor this instead of having to do my x method. When I see these two terms, I'm going to do an x plus 5 times an x minus 5. Now, knowing this property is super important because remember, when we're looking at factoring, first we look for our greatest common factor, and I don't see one here. The next thing we do is we have to count our terms. And if I only count two terms, what that means is it's going to follow one of these special product properties. It has to, because these ones have two terms. There are some special product properties that apply to a trinomial rather than a binomial, so it has three terms. When it has those three terms, we can actually use that x method, just like we were doing before. Or we can use this pattern to factor it in a faster way without having to do the x method. It's totally up to you. But whenever we see these two terms, we have to use one of these special product properties. So there's our example of this first one. This next one, 4z squared minus 1. Well, I want to know, I have my difference here, so that works. Can I multiply two of the same thing? Is this a square? Yes, 2z. That doesn't look like a z, that looks like an e. 2z times 2z, well 2 times 2 is 4, z times z is z squared, will give us that. And our 1 is just going to be 1 times 1. So when I expand this, I have 2z plus 1, and I have a 2z minus 1. That's what that's going to expand to. So I want you to use that special product pattern here to evaluate what this expression is going to be. So notice how this one has numbers instead of variables. All it means is it's going to follow the same pattern. So when we ask what the solution to an expression like 54 squared minus 48 squared is, I don't know what 54 squared is without a calculator. You probably don't either. But I can use this special product pattern to simplify the problem. Instead of doing 54 squared and then 48 squared and subtracting it, I can say I know this is going to be the same as 54 plus 48 times 54 minus 48. And when I do that, 54 plus 48 is going to be 102. And 54 minus 48 is going to be 6. And I can multiply these, and I'm going to end up getting 612. And I don't even need a calculator to figure that out. I mean, I might want to use it, but I don't have to. I don't have to type in 54 squared and 48 squared and then subtract those. I can use this special product pattern to simplify problems like that. Now, I want you to take a chance to go over these. What I'm going to do is I want you to pause the video, try all 4 of these examples on your own, simplify them, take however long you need to. Once you've finished answering all 4 of these questions, unpause the video, wait a second, and then what you're going to see is those solutions worked out for you so you can check your work. So go ahead and pause the video now. Okay, hopefully you have the chance to work through these problems. Going over these quickly, x squared minus 36. Well, that x squared is an x and x square. 36 is the square of 6's, so we get x plus 6, x minus 6. 100 is the square of 10's, m squared is the square of m's. Now notice how this is 10 plus m and 10 minus m, not m plus 10 and m minus 10. The order here does matter. So if this 10 is written, the 100 is first and it breaks down into a 10 and 10, the 10 has to be our first component in these binomials. We can't switch the order. And 9n squared breaks down into 3n times 3n. 16 is 4 times 4, so 3n plus 4, 3n minus 4. And this 16h is h squared minus 49 breaks down into 4h plus 7 and 4h minus 7. And that's how we would factor using this difference of two squares patterns. Now, there are two other patterns that we are going to talk about, and these are called the perfect square trinomials. And what happens is these are the ones that are going to factor out into something like x plus 4 squared or x minus 7 squared. And these are going to follow this pattern right here, where it's going to be our first term squared plus 2 times the other terms plus b squared. Now, when you observe something like this, then we can use this pattern and we can simplify it. If for some reason you don't feel confident in observing this pattern, we can still use our x method to solve these. So what we want to do is we want to look if it's 2 times something or 2 minus something. So this first one, do you see how it has a plus here and a plus here? What I want to look at is what are my A, B, and C. In this case, A is 1, B is 8, and C is 16. Now, if this follows our rule, this will be 1 squared, this will be 4 squared, and this will be 2 times 1 times 4. What is 2 times 1 times 4? Well, that equals 8. So this works. So instead of writing this and doing my x method, where I find what numbers multiply to 16 and add to 8, what I can do here is I know that this is going to end up being x plus 4 squared. And the reason why I know it's going to be this plus is because our 8 was positive. Now let's take a look at part B here when we're looking at our A, our B, and our C, just like we were before, A, B, C. So A, well, does that break down into, is that a square number? Well, yeah, 4 is 2 squared. C, is that a square number? Yeah, 9 is 3 squared. So that means in order for this to work, our B needs to be 2 times the square of our A, so 2 times 2 times 3. And what is 2 times 2 times 3? Well, 2 times 2 is 4. 4 times 3 is 12. Now notice how I have a negative 12. So the negative 12 clues me in that up here, when it's a negative, the inside is going to be a minus. If it's a plus here, the inside is going to be a plus. So here I am, and I can rewrite this as x minus 3 squared. 2x minus 3 squared. Notice how our a goes there, because this really breaks down into 2x times 2x, right? So it's going to be our 2x minus 3. So 4x squared breaks down into that 2x squared. So that's how we would break it down. If we wanted to use that x method, we totally could on all of these. So remember, if our a is greater than 1, then we have to multiply them. So 4 times 9 is multiply to get 36, add to get negative 12. So then I could write out my factors of 36 here, and I would have 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. Or I also have all my negative ones, so negative 1, negative 36, negative 2, negative 18, negative 3, negative 12, negative 4, negative 9, negative 6, and negative 6. And notice this is going to be our negative 6 and our negative 6. So I have a negative 6, but I multiplied it by 4. So I have to divide it by 4, divide it by 4. These simplify to a negative 3 over 2 and a negative 3 over 2. So notice when I wrote that, I ended up with a 2x minus 3 times 2x minus 3, and that can be rewritten as 2x minus 3 squared. But look at how much work this is. We can do that work, or we can recognize that this might follow that pattern and do it that way. So I want you to take a second to factor all three of these ones. Decide, is it going to end up being a plus b squared, in which case it's going to be a squared plus 2ab plus b squared. So check to see, are these two terms here going to be squares? And then if they are, does this middle term work out? Or is it going to be an a minus b squared because it's a squared minus 2ab plus b squared? So again, we're checking to see if that first and last term are squares. If they are, we want to check to see if the component that's a square of them, so if it's 4, is 2 times whatever the other one is, going to give us that middle term. And if it is, then we can use this pattern. So go ahead and pause the video, go through these. Once you finish going through all the examples, or as many as you want, unpause the video, wait a second, and I will have the solutions worked out for you. Okay, hopefully you had a chance to look over those. So when I do these, I like to break them down this way. I check, is that first term a square? Yes, it's m times m. Is my second term a square? Yes, it's 10 times 10. Is 2 times my first term times that second part of the term, so 2 times m times 10 can be 20m? Yes. Now, because there's a negative sign here, that means I'm going to have a negative sign in the middle. If it's a plus sign, like we see over in example number 3, then it's going to be an addition sign. There are those examples. Those are the 3 types of special products that we need to know how to factor in this class. As we go throughout math, we're going to learn how to factor special products of cubes. We might learn how to factor other special products, but for this class and for the sake of our assignment, the ones we're going to focus on are the difference of 2 squares pattern, as well as the perfect square trinomial pattern. And that is how we're going to factor these special products.